and that is solving trig equations. We're not solving trig equations yet. You made it. Right. You even signed.
I already signed up.
Yeah.
I gotta be here.
You got to be here. Let's talk about solving equations. You're given the equation x plus 1 equals 10. What allows us to solve equations is that you have inverse operations, operations that undo other operations. So how do you solve this equation? Well, since there's addition involved, we have this inverse operation called, subtraction that allows us to solve the equation. And then later on with your more advanced equations that you have, if your equation dealt with squareds, quadratic equations, you have this inverse function called square root that undoes squared, right? That way you can get the variable by itself. So where we're headed with all of this is, okay, if I have a trig equation, where now you're being asked to find me the value of theta, or values, could be more than one, find me the value of theta that I can plug in here to make this a true statement. As you're about to see, we'll get the sine of theta all by itself, so we'll subtract 1 from both sides. We have to come up with these inverse trig functions, meaning I'm going to take the inverse sine of both sides. We're going to define the inverse sine today. But as you can see, we need these inverse functions, because what happens on the left-hand side? Just like square and square root cancel each other out, just like addition and subtraction cancel each other out, sine and inverse sine cancel each other out. And we're left with theta equals whatever this ends up being, which we're going to talk about those now. Make sense? So give us the tools for solving trigonometric equations. Now, before I can talk to you about the inverse trig functions, I have to go back and review with you from algebra what a one-to-one function was and why they're necessary. Remember that a one-to-one function is a function that passes the horizontal line test. For example, if I give you the function, let's let f of x be just plain old square root of x. What does that graph look like? Rough sketch, square root of x looks something like this. It's a function because it passes the vertical line test, but now we can say it's a one-to-one function because it passes the horizontal line test. And what's important about a one-to-one function is that one-to-one functions have inverses. How do you find the inverse? Well, we take y equals square root of x. Y equals the square root of x. And remember, how do you find the inverse function? You switch x and y, and you solve for y. Solving both sides or squaring both sides, we get y equals x squared. So far, what we're saying is y equals x squared should be the inverse function to y equals the square root of x, and that is not totally necessarily correct. If the purpose of an inverse function is to switch all of the x's and y's, it also switches the domain and range. And if you go back to your original function, f of x equals square root of x, there the domain is what? From 0 to positive infinity. What's the range? Also from 0 to positive infinity. So you have to switch those, and the domain of f becomes the range of the inverse. And the range doesn't make a difference with this problem because they're both the same thing. But down here we would get domain and range also 0 to positive infinity. So this isn't necessarily true, folks. The entire function y equals x squared is not the inverse to square root of x. It's this part of y equals x squared. We have to limit the domain. We have to take this part of the function away. Now we're correct. Y equals x squared is the inverse function to f, but you have to restrict the domain to only being from 0 to positive infinity. Okay? Makes sense. I mean, think about it in reverse. What if I would have started you off by saying, okay, here's y equals x squared. What is the inverse function? Well, you would say, hey, y equals x squared is a parabola. It's not a one-to-one function. It fails the horizontal line test. It does until I take this part away. If I'd say, let's pick on y equals x squared and only talk about this domain, does it have an inverse? Yes, it does. This function right over here. See what I mean? So if a function is not one-to-one, you can maybe limit or restrict the domain so that part of it is, which is what we do with our trig functions. Think about the sine curve. Think about the cosine curve, right? Clearly not one-to-one functions. They're going to fail the horizontal line test. So, what we do for the inverse sine function is you and I restrict the domain to these values. Only negative pi over 2 to positive pi over 2. This part in blue, folks, of that curve, that part in blue, only the part in blue, that would be a one-to-one function. That part would pass the horizontal line test. Okay? So if we take f of x equals sine x, the sine function, and limit the domain from negative pi over 2 to positive pi over 2, what's the range? That stays the same as normal sine function with all real numbers being the domain. That's still from negative 1 to positive 1. Now, this we can find the inverse of. This part of the sine curve is a one-to-one function. So you and I are going to define f inverse. What's the inverse function of sine x? We call that inverse sine of x. Okay, and the inverse sine function, again, switch the domain and range of our original function. The domain will be from negative 1 to positive 1, and the range must be values from negative pi over 2 to positive pi over 2. Okay? And think about angles. Think about angles that go from positive pi over 2 to negative pi over 2, right? Positive pi over 2 means go that direction. Negative pi over 2 means we're going to go in this direction. So please make a note somewhere in your handout that inverse sine function, you are always dealing with a quadrant 1 or quadrant 4 angle. Quadrant 1 if it's positive, quadrant 4 if it's negative. All right? Once you start seeing how we're going to use the inverse trig functions, then you'll be okay with this. Some examples. Oh, I'm sorry, I got ahead of myself. There's alternative notation also for inverse sine. You may write it one way or the other. Arc sine of x is the same thing as inverse sine of x. But what is important is that the answers that you give must be between negative pi over 2 and positive pi over 2. So letter A says, find y in each equation. So here we have y equals arc sine 1/2. So what I like to do is I rephrase the question. Arc sine means answer is an angle, right? Plain old sine function, plain old y equals sine x. You plug in angle, out comes real number. Well, see, now we're swapping those roles. We're plugging in a real number. We're trying to figure out what angle causes that real number to happen. So another way of thinking of A, letter A, is what angle has a sine of positive 1/2? Now remember, arc sine, that inverse circular function, the answer that you give must be either a quadrant 1 angle or a quadrant 4 angle. Since the 1/2 is positive, right, we're dealing with quadrant 1. So what angle has a sine of 1/2? you would answer that as pi over 6. Pi over 6. Pi over 6 is between negative pi over 2 and positive pi over 2. Careful how you answer the next one. What angle out there between negative pi over 2 and positive pi over 2 has a sine of negative 1? What would y be in this case? It's negative, so it's quadrant 4. So what angles do you know of that have a sine of negative 1? Or what is the angle that you know of that is a sine of negative 1? What do you want to say?
3 pi over 2.
You want to say 3 pi over 2, but what is that in relation to the range of the arcsine function? What's this angle right here again? 3 pi over 2 is the same thing as negative pi over 2. Going 3 pi over 2 radians in this direction is the same thing as going pi over 2 radians in the opposite direction. So you got to give the answer in terms of the range of that function, which is negative pi over 2 to positive pi over 2. How about C? What angle out there has a sine of negative 2? Well, what's the domain, guys? What's the domain of the inverse sine function from negative 1 to positive 1? That's not in the domain, so you would say does not exist. Can't do that problem. Okay? Questions, concerns, comments, or complaints? We're going to do this all over again with the cosine function, and then we're going to assume that we can continue on with this with all the other trig functions. But again, to start the story over again, clearly you can see that the entire cosine function is not a one-to-one function. So we just highlight again part of it that is. And with the cosine function, we're going to restrict the domain from 0 to pi. So if f of x, oh, by the way, if you printed this stuff out early, you're not seeing, I added this yesterday or this morning, I can't remember. So just bear with me. Bear with me. You do have the chart that's important, that summarizes all of the trig functions. So if f of x is a cosine function, we're going to limit the domain to be from 0 to pi. The range of this function, again, like before, negative 1 to 1. Now we're going to switch the roles. Inverse function, which we're going to call arc cosine or inverse cosine. The domain of the inverse function will be negative 1 to 1. And the answer that gets kicked out, 0 to pi. What quadrants does 0 to pi put me in? 1 and 2. Quadrant 1 or 2. Okay? I'll tell you right now that the 3 inverse trig functions on your calculator give you the correct angle in the correct quadrants. Be very careful if the question wants your answer in degrees. You can go in and put your calculator in degrees. It gives you the correct answer. Or change it to radians. It will also give you the correct answer. So in terms of arcsine, arccosine, and arctangent, the answer that you get from the calculator is the correct quadrant. The other 3, inverse cotangent, inverse cosecant, and inverse secant, the answer that you get may not be the correct answer. We have to change the problem a little bit, and I'll address that a little bit later. All right, same thing as before. I'll give you some examples. Here we're dealing with inverse cosine. So now I need to be thinking quadrants 1 and 2. Quadrants 1 and 2. Remember that the range is 0 to pi. For let's list that up here. My answer for these two problems, the range of the inverse cosine function goes from 0 to pi. What angle from 0 to pi has a cosine of 1?
32. Never mind.
What angle from 0 to pi has a cosine of 1? Nope. Just 0. Pi would be negative 1. So here we would say y is equal to 0. Again, this might also help. If the inverse trig functions are new to you, another way I think of this is I rewrite it out like I'm used to seeing it. Y equals arc cosine 1 is the same thing as saying cosine of what angle, in this case y, right? The cosine of what angle is 1. If you think of it that way, it might help you solve these problems a little bit easier. Either way, you would say that cosine of 0 is equal to 1. Letter B, since this guy is negative, we're in quadrant 2, right? What angle has a cosine of root 2 over 2? 45 degrees or pi over 4. What would it be in quadrant 2? 0 to pi, 0 to pi, 0 to pi. What's pi minus pi over 4? Right? You're over here. Here's pi. You're going to go back a reference angle of pi over 4. So 4 pi over 4 minus pi over 4 is 3 pi over 4. That's the angle, guys, that's between those two. It's in that interval. So the chart that I mentioned earlier, that I'm sure this is on your handout. This not only summarizes the two that we just talked about, arc sine and arc cosine, but it gives all of the other ones. The column that you should pay close attention to is are these two columns, because that's telling you what your answer needs to be between and what quadrants are involved. Okay? Now let's practice a couple of the weird ones where a calculator may not give me correct answer right off the bat. Got two examples here. Example says find y in radians if y equals arc cosecant of -3. And what I found was if I write it out thinking in terms of writing it out as, okay, arc cosecant of -3 is this angle y. I put it in perspective, okay, the cosecant of what angle is -3, right? That's what you're finding. And let's get rid of cosecant. Let's put it in terms of sine, cosine, and tangent. Let's take the reciprocal of both sides. What's the reciprocal of cosecant y? No, the left. What's the reciprocal of cosecant? Sine. So this is the same thing as sine of what angle is -1/3. Again, all I did was take the reciprocal of both sides. And our calculator has inverse sine function. Letter A says, find me this angle in radians. So I'm going to hit the mode button, make sure my calculator's in radians. And then I'm going to say, calculator, inverse sine. So second button, sine button. Inverse sine, -1/3. And there's your answer in radians. -0.33, however many decimals you'd want to go. -0.3. Probably should go out to 33983. 33983. Right? Questions with A? Good. B, do the same thing. B, notice they say find your angle in degrees. So let's go change our calculator mode to degrees. Okay. And again, we'll put this in perspective of the reciprocal. B is asking us to find what angle has a cotangent. Cotangent of what angle is negative 0.3541. Take the reciprocal of both sides. The reciprocal of cotangent is tangent. And on the right-hand side, the reciprocal would be negative 1 over that decimal, 0.3541. Okay? So, calculator. What angle has a tangent of negative 1 divided by 0.3541? And we get negative 70.5 degrees. But that is not technically correct yet. Here's what I meant by with these reciprocal functions, the calculator answer may or may not be the correct answer. The original question was what? Arc cosine. So my answer has to be in what two quadrants? So I go back up to my chart. I say arc cosine, which is right, I'm sorry, what did I say? Arc cotangent we're working on, right? That's this guy right here. I need a quadrant 1 or 2 angle. Quadrant 1 positive, quadrant 2 negative. So if I'm dealing with a negative 70.5 degree angle and it's in quadrant 2, what would that be equivalent to? Again, here we go, 0 to 180. I'm going to go back this way, 70.5 degrees. So it's,
29.5.
what's that? No. 180 minus 70.5.
119. No, 109. 109.5.
109.5 degrees. There's the answer this question is looking for. So I can't stress enough early on, have that chart there beside you telling you what quadrant your angles need to come from.
Is that in our book?
The chart? Yeah. I pulled it right out of your textbook.
So we can use that on the test?
No. All right. Moving on. Here you'll see that after you start working with these a couple times, you'll start remembering the quadrants. Remember, you'll be thinking arc sine 1 and 4, arc cosine 1 and 2, and tangent arc tangents back to 1 and 4 again. Those are the 3 you should know. All right. I'm not big into giving you arc cosecant questions. All right. These problems are unique. These problems say, or are saying at the same time, we want you to find an angle. Remember, arc inverse trig functions, the answer is an angle. So what I have highlighted, guys, this part of the problem right here, that's an angle. That's an angle. So with this one problem, they're asking you to find an angle and then turn around right away and then take the sine of that angle. All right. Here's how we go about it. How do we come up with the angle? Well, I see I'm taking inverse tangent and I have something positive. So what quadrants that put me in? Oops. Inverse tangent, and the 3/2 is positive 3/2. That's going to be quadrant 1. So my angle is in quadrant 1. So let's draw the right triangle. And what else do we know about this angle? We know that its tangent is 3 over 2. We know that y over x is 3 over 2. So y is 3, x is 2. So what would r be? Well, 3 squared is 9, 9, 4, 13, square root of 13. We have no idea how many radians that angle is. We have no idea how many degrees that angle is. I don't care what it is. We don't need it. That's the angle that we're talking about. We found the angle. What are we going to do next? We're going to turn around and take the sine of that angle. Sine of this angle that I have drawn here. So the sine of this angle is y over r. In this case is 3 over the square root of 13, which we rationalize to get 3 root 13 over 13. So there's the final answer to this problem. And check that out. You never at one time had to actually come up with the specific angle measure. You're just using the right triangle. So using that problem as a model, try letter B. Try letter B. Okay. Here we're being asked to find the tangent of the inverse cosine of negative 5/13. So let's first try to identify where this angle is. Arc cosine, quadrants 1 and 2. And since it's negative, means we're in quadrant 2, right? So here's some angle in quadrant 2 whose cosine is negative 5/13. Cosine is x over r. So that must mean that r is 13. X is negative 5. And what's the missing side? 12. So there's the angle. Whatever that angle is, that's this angle. Now we're going to turn around and take the tangent of that angle. Tangent is y over x. We get 12 over negative 5. There's your answer. All right? Are those two problems, you guys are comfortable with those? Because now we're going to make it slightly more difficult, incorporating some things we learned from the last chapter. You all right, Josh?
Yeah.
I asked a question. Sorry.
It's fine. Here's how we're going to make it more interesting. Let's incorporate some of your other identities, like cosine of a sum, sine of a sum, double angle, half angle identities. First thing you have to visualize here, folks, is that letter A is nothing more than the cosine of a sum, right? This arctan root 3, that's an angle, angle A. This arcsine of 1/3, that's just an angle, angle B. This is nothing more than the cosine of A plus B. So we're going to write out that identity. Okay, so we're looking at cosine A, cosine B, minus sine A, sine B. That's what our identity says. Now we'll take out the A and the B and actually replace them with what they are. Yes, it gets kind of messy. Cosine A is the same thing as cosine of arctan of root 3 times cosine B, cosine of arcsine of 1/3 minus sine A, sine of arctan of root 3 times sine of arcsine of 1/3. And then each one of those, right? Each one of those is just an example of our earlier problems. Some of these are a little bit easier than others. Let's get in and see what happens here. Let's take a look at the first one. Arctan is quadrants 1 and 4. So what angle out there has a tangent of square root of 3? What angle has a tangent of square root of 3? Nope. That'd be 1. Pi over 3 or 60 degrees, right? So what I have an underlined is the same thing as cosine of pi over 6. Arctan of root 3 becomes pi over 6.
Just 30 degrees.
30 degrees, right.
36, 60.
Now let's take care of this one. Well, this one, because 1/3 isn't one of our, it's not the trig function of a special angle. Root 3 was a special angle situation. 30, 60, 45. We don't have that with the 1/3. So for the part that I have a double underline under, there's where we have to go up here, draw the right triangle like we did with the last two problems. Arc sine being positive, that's quadrant 1. So I have this angle up here in quadrant 1 whose sine, whose y over r is 1/3. Now I got to use the picture to find x. So 3 squared minus 1 squared, 9 minus 1, 8, square root of 8, 2 root 2. So the x value would be 2 root 2. So let's turn around now. Let's turn around and take the cosine of that angle we just found. And cosine is x over r, so we're going to be multiplying by 2 root 2 over 3. Are we okay with the left-hand side of the subtraction? Right? On the right-hand side of the subtraction, we got to draw a triangle for this one. Or wait, no we don't. I'm sorry. No, we don't. Arctan of square root of 3 is the same as earlier. That was pi over 6, right? So this will be minus sine pi over 6. And then the last one's easy. Sine and arcsine, right, are inverses of one another. They cancel each other out. So the sine of the arcsine of 1/3 is 1/3. That's like saying take 2, square it, and then take the square root. You're back to 2 again. A couple more steps and we're finished. What's the cosine of pi over 6? The cosine of 30 degrees. Root 3 over 2. We're going to take that times 2 root 2 over 3. Wait a minute. The cosine of 30 degrees is 1/2. That should be 1/2. The cosine of 30 degrees is 1/2. Minus the sine of 30 degrees. There's where we have root 3 over 2 times 1/3. So we'll keep on going with this. Multiply becomes before subtraction. So 1/2 times root 2 over 3 is 2 root 2 over 6. Minus, multiply together, we get root 3 over 6. We have a common denominator. So our answer is 2 root 2 minus root 3 all over 6. There's the exact answer to letter A. I'll give you a moment to stare at that if you have any questions. All right? I'm going to have you try B. I'm going to erase this. Does anybody have anything they need to write down before I erase it? And to get you started on the right track, when you look at B, what is that in disguise? Which identity? It's a double angle identity. It's the tangent of a double angle. So go ahead and try to figure out what that angle is. and then use your tangent of a double angle identity. Okay, so we'll find the angle first. Whatever this, and I labeled it angle A. Let's just call this, right, tangent of 2A. And I draw the picture. Here's the angle, quadrant 1, that has a sine of 2/5. Did you get your missing side to be the square root 21? Right? So now the tangent of that angle, the tangent of angle A, y over x, would be 2 over the square root 21. Yeah, I know that needs rationalized, but I did all that at the end. So let's just keep it 2 over the square root 21 right now. If you didn't, if you went ahead and rationalized at the beginning, as long as you did the correct arithmetic and algebra, you should end up with the same correct answer. So we're using the double angle identity. Tan of 2A equals 2 tan A over 1 minus tan squared A. And we're going to simply substitute 2 over the square root 21 in here for tan A, and also in here for tan A. So we end up with 2 times 2 over root 21 over 1 minus 2 over root 21 squared. And the numerator, right, we take 2 times 2 over root 21. That gives us 4 over root 21. And down below, let's see what happens. We'll square this fraction first. Means we square the top, we square the bottom. That gives us 4 over 21. We then need to get a common denominator, so 1 is 21 over 21. 21 over 21 minus 4 over 21 gives us 17 over 21. So at that point we have 4 over root 21 over 17 over 21. And what I did next, here's where I rationalized. I said, okay, now the numerator is the same thing as 4 root 21 over 21. And now we're going to multiply that by the reciprocal, which is 21 over 17. The 21s cancel out, and you have 4 root 21 over 17. So again, the algebra made that, I think, difficult, not the trig. All right?
Close to 4/3.
Close to 4/3. Okay. Now, purpose of working with all these inverse functions. You're now to the point where it's time to solve trig equations, and your text